All right, here it is, final video. I'm going to start off, I think, just by showing all of the various demos that I've thrown together here to demonstrate everything's working before we dive into documentation and code and all of that good stuff. So first thing I'm going to do is, you mentioned in the grading checklist that you wanted to see for certain that scene switching, especially with factories, actually worked. So here we have the basically the same demo that I used, the general everything thrown together demo from last year, but we've got ourselves scene switching here with the God Cam. You can see the tiered collision going there, but we've got ourselves some box factories as you'll see down here, and if I switch scenes, I'm sorry, I gotta go up and check through all the destructor messages, but you'll be able to see all boxes deleted here as the scene destructor is getting called when it's switching to a new scene. It recalls all the boxes to the factory and then deletes through all of them. So there's that, and then we can switch on over to the new subsystems more specifically. So we'll go ahead and start with the collision. You saw a little bit of the tiered system to begin with there, but here we've got the collision. You'll see the large yellow AABBs for the groups, and then testing between the two orange base B spheres here. When they collide, then testing between the two uh, closer collisions. In this case, the box only has a B sphere colliding with the oriented bounding box here. So self collision works the same way. As you can see here, B spheres first, then closer the closer check. Ding, there it is. Obviously, because self-test doesn't have the group ABB to call earlier, that doesn't exist for that particular test. So the terrain is next up here. We've got terrain being loaded in and created here. I can zoom in a little bit and you can see it is indeed being created by a height map. It's got some lovely little mountains here. You'll see the public methods are working as well. The projecting the center of the ship onto the terrain and getting the normal from the terrain. I just have the normal set to a length of 50, but as you can see, it changes based on whichever triangle you are inside of at the point. And then if I zoom back out, you'll be able to see that colliding with the terrain works as well. It's set up so that the group AABB collisions are, the AABB to AABB collisions are yellow, B sphere to AABB collisions are orange, and then actual close collisions are the red squares. So you can see that the hierarchical structure works all the way across the board here. All right, next and finally is the AI actor demo. That's going to be the little AI turret here. Circles around until my player ship here gets within 100 units of it, and then it starts firing. And then as soon as you leave the space again, it switches back to the patrol mode. All right, next up, we're going to dive into the code here a little bit. We're going to start with the collidable system. So here's the collidables class. Fairly standard just game object component. It's got the collision callback and the collision terrain callback. Both of these sent through at the proper time by the subsystems that I'll get into later. The register and deregister methods deal directly with collidable groups. and obviously the protected functions for setting a bounding model. You'll see here I have it done through Ed's enum trick. The bounding sphere type, bounding type ABB or OBB determine which setup method will be used for the collidable itself. But once that is done, there's only a single update data that that needs to be dealt with. There's also a couple easy methods for rendering the tight collision volume that the user's chosen, or rendering the base sphere that every collidable does have here. So I'll go into the class diagram here for the main subsystems. So we were just looking at the collidable. Collidable obviously has two bounding volumes attached to it, both the base bounding sphere as well as whatever the user defines at the moment, probably an OBB or AABB bounding box. As you can see, the hierarchy here with the OBB and AABB both being derived from the bounding box superclass makes it easier to do collisions between the two. I'll show you that in a little bit when I get to the math tools. But like I mentioned, so when you register a collidable for collision, it sends its data to the collidable group. Registering here in the priv register function to the list of active objects that is inside the collidable group. Once that is done, the collidable group in its update uses that list to create the group AABB culling volume. So what it does is just takes the base sphere of all of the active objects, takes the center plus the radius and takes the center minus the radius, figures out what's the max of all the max points, what the min of all the min points is, and creates the rough collision AABB out of that. Also, let's see. Right, so that is the collidable group. That is a singleton, as you can see through in here. All of these are static functions that are passed through to the instance, which means there's no real person in charge of updating or deleting these things at the proper time. That would be the collision manager's job. So if we go back to the system diagram here, the collision manager holds a command broker for destroying commands, so destroying the collidable groups when the collision manager is done. The update command broker that handles the updates every single frame, and the active tests runner. So that's the one that holds all the collision commands, the collision pair, collision self, collision terrain commands, and processes them through every update tick. So using the scene level register for collision commands, the register for collision methods, those commands are put into the collision manager here. So the register collision pair, self, or terrain create a new commands on the test runner, and those are processed through as normal. Whenever a new group is created, that's also sent into the collision manager and adds in the destroy and update commands, processes them through as normal. So for the actual collision tests here, we've got a good tiered system. So we get the collidable group of the group 1 and group 2, checks to see if those two AABBs collide. If they don't, then there's no reason to do any of this other stuff. We can break right out. If they do, we start iterating through the collections of these collidable groups, and they are passed in as pointers. No copying needs to be done here. So we get the front, start iterating through, check if each one's bounding sphere collides with the rough ABB of the second group. If it does, then we check all. Then we start checking through the second group's objects to see if they collide with the first group's ABB. I haven't done exactly the math on this extra step, but just going through the mental process of checking these things over, it doesn't save any time when there's only a single object from the first command intersecting the second command, but when there gets to be 3 or 4 first group objects colliding with the second group's ABB, calling out the number of objects, calling out a number of objects in the second group gets rid of a lot of pairwise tests that we'd have to do if we were just to say all of the group 2 objects start getting checked against the first group ones that are colliding with the second group. So after all that, once we have 2 objects that we know are occupying the same AABB space, then we do a sphere collision, the cheapest collision between actual bounding volumes that we can get. Once we've done that, then we go ahead and move into the potentially expensive close collision test, the one that's defined by the user. The self collision is essentially the same thing. It just cuts out a lot of steps because we don't have the group AABBs to define by. They are both objects will be by necessity inside the same group, so we can't use that as a pre-calling method. So we just simply check base spheres. If they're colliding, then we move ahead to the expensive test. As you can see here, we can use the first iterator to add to the second iterator, so there is no possibility of self-collision. We start with 1 on this loop, and we start with 2 on, or we start with 1 plus 1 on this the second iterator. So the terrain test is very similar to those again, but we get into the cell collection here. So this is the specific collection that I've defined to separate my cell collection iterator from my terrain object. It's not an actual like standard collection. It's just so the cell collection, this class here actually holds indices for the first item and the last item that the iterator will be moving through, and translates from the iterator's single index value into the exact terrain cell that is supposed to be represented by that iterator. But from the command side, it just looks very much like a regular iterator. Starts at the beginning. When it's not at the end, iterate through. This one checks to see if the group AABB collides with a cell. If it does, we check the B-sphere colliding to the cell, and then if the B-sphere collides with the cell, then we check to see if the tight the tight user-defined collidable volume collides with the cell. If it does, send in that callback. So obviously the intersect and the collision methods here are a pretty important part of this whole deal. Obviously, that is helped out by the math tools, which has been the math tools class much improved since last quarter. We have the basic stuff that we used to have: min, max, in interval, overlap, clamps. This is new, the projection. We have a point projection onto a vector. Point in B-sphere, point in AEBB, point in OEBB, and then we start getting into the collisions here. So bounding sphere to bounding sphere collision, fairly simple. AEBB to AABB, also fairly simple. Check the intervals. We have the collision bounding sphere and a box, so that we just can clamp the bounding sphere center to the box, and if that new clamped point is still inside the sphere, then they're colliding. And then we get on down to the complicated one. So box collision can be used between any OBB to OEB or OBB to AABB. And that is the 15-axis test here. I do a little bit more complicated, but a little bit more performant method of checking the half diagonals. So as you can see, I haven't done it all in a single method. The box collision method creates all the axes that we need to test along, and then checks to see if they have a separating plane. Because obviously if there is a separating plane along the axes, then there is a gap between the boxes, and therefore they're not colliding. So the check here is if the maximal half diagonal projection is greater, or if the distance between the centers of the two boxes along the axis that we're testing on is greater than the sum of the maximal half diagonal projections of the two boxes, then there is a separating plane. So again, this method's broken up to the maximal half diagonal projection method that gets the actual the distance of that half diagonal projection. So the actual math is done here, which is sent up to the has separating plane, which is sent up to the actual test here. And then we have OBB to bounding sphere, obviously, at the end. So another important part of this whole collision system is the visualizer. Very hard to debug your collisions if you're not able to see what's exactly going on. So the visualizer is also much improved this quarter. Not only do we have a render B-sphere, we also have render axis aligned bounding box when passing in a box. Also when passing in a min and max point. That's particularly useful for the terrain because I only save the min and max point of the cells. Render an OBB, obviously. We also have just to make it easier to test the math tools functions, we have the render point and render a line segment here. And so the actual code for all of these things is fairly simple. We get the scale and rotation and translation of what the box that's being passed in is, and then we take our unit box here, send it through, and then obviously when we're done with the visualizer, get rid of that nonsense. Hello, have we not deleted our unit sphere? Unit box, that's what we haven't deleted. All right, then next up is we're going to do terrain and my AI project, and then we're going to go over a little bit of the documentation. So first off is the terrain. Here we have actually let's go to the diagram first. Sorry, it's on the whole diagram, but so we've got, on the scene level, we've got a terrain manager, holds the current terrain object. Um, that terrain object uh, will create cell collections as necessary, and those cell collections are able to return iterators through that cell collection. So what the terrain object is the loaded in from the file. So if we go into the asset managers here, we've got a terrain load manager that will set the terrain. Where is it? Yeah, set terrain here. So you input the key you want your height map from your file. If I have a special assets folder for height maps, so all you need is the path if it is deeper than that, otherwise just the file name. And then the side length, max height, zero height, texture key, the previously loaded texture that you want to apply to the terrain, and then the repeat U and repeat V value for the number of times you want it to repeat along X and Y. And then those are passed into the terrain object creation here. If I scroll on down here, creating the terrain model, which will, first of all, check the height map file, the repeat U, the repeat V, to see if the model has already been created once. If it has, then there's no need to go through the entire fill, vertex buffer, vertex array, save out to a file, save back in, because it already exists. So all that is needed is to just add it back in. Obviously, if it doesn't exist yet, then all this needs to be done, checking in each individual pixel to a vertex, saving it out as a model. I do it saved out as a unit size model 1 by 1, and then scale it at the end by what the user decides here. So first it's created, saved out to a file, loaded back in, and then the actual graphics object is created here. Then scaled out by whatever the user has defined. In the process of which we have a collection of cells being created. That happens regardless of whether the model is already created or not, just because every terrain object in the engine needs to have its collection of cells. So we iterate through the cells per row, cells per column, creating the cells out of 4 vertices. Moving on down the line, creating the triangles as well as we're doing it. Getting the min and max point. Let's see, where is that terrain object? Where is yeah. So the terrain cell is not a very lot of data. Obviously, we're going to have a lot of them, so try to keep it small. Just a couple integers, the vectors of the min and max in the world center, and then the index of the top right and bottom left triangle. That's useful for some of the public accessors that we have available to us. So projecting a point in the world onto the terrain requires us to know. Go to definition, please. It requires us to know what triangle we're looking at here. So I have accessors for the world position, the cell index that's pointed to by this world position. From there, I can test the triangle, see which one's closest to it, and then from there, use the ray plane intersection to find the exact point where the on the model where the point in world space would be. This is, of course, clamped to the side of the terrain, so going off the edge of the terrain in any of the directions will just pull that point onto the terrain. Because that kind of breaks ray plane intersection if they don't actually intersect. The Y value is a little bit off when you go off the side of the terrain, but nothing crashes. That's the important bit. Um, kind of related to that, we have the normal at world position, which basically does half the work that project onto terrain does. It doesn't need to actually do ray plane intersection. It just needs to find which triangle we're dealing with based on the world position. And then from there, it just asks what the normal of that triangle is. We also have, important for collision, we have the cells under method. So this one is finding what the cell of the min point and max point of the passed in AABB volume is, and then creating a cell collection of that same size. So a cell collection just takes in the numbers that you pass into it and allows the access to the iterator through that collection. So I have the iterator and the terrain object completely separated. The iterator has no knowledge of the terrain object or any of its internal arrays, and the terrain manager doesn't know that it has a collection that can be iterated on. The cell collection is this middleman class. So when you want to dereference the iterator, here, it calls the cell collections at whatever index it is, starting at 0, going up to the number of cells in the collection. So then the cell collection interprets the iterator's index and finds the actual cell that it is pointing to. So that's all wrapped up into the terrain object. The terrain manager, which is this scene level manager that controls which terrain is being set through and passes in the render command here, is pretty simple. On the user side, the scene just calls set terrain with the key of the terrain that you want here, and that goes into the terrain manager, sets current terrain to be the one that you want, and will process through the render command. As you'll see here, I didn't get a chance to iron out all the intricacies of creating a null object for this terrain, so it has to have an if check for if a terrain's actually set, so we don't crash at the first frame every time because there's no terrain and we're trying to render a null object. So I already described to you back in the collision section a little bit about the collision with the terrain, so we'll go ahead and move right along into AI. So my AI actor, like I described in class the other day, is just another game object component. The basics of basically the only thing that differentiates it is it has a behavior tree, this little class here that holds a root node. So the way this whole system works is it's made up of nodes and goals. Man, I've opened a lot of things. So behavior tree, nodes and goals. This basically works like a hierarchy. So the node root allows you to add a single sub goal underneath it. The um, hmm, the the manager for all the AI, boop, 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 actor manager, will simply process through, send the update tick in to the root node at every update, which will process the first added sub goal of the AI's behavior tree. The user, as as I showed in my actor demo here, so the user will create generally a node um, that will be processed at the beginning of every frame by the behavior tree. That node can then become a nested hierarchy of its own. So for my turret demo here, we have the sub goal of a turret watch, which is its own complex node, and then a goal of turret patrol. So there's two different kinds of nodes, the node selector, and turret watch is one of these, a node sequential. If we go back to turret brain here, so node selector means that it breaks out and finishes when it reaches its first success. So this is a kind of if-else statement. If the turret watch fails, then it defaults to patrol. If on the other hand, the turret watch is node sequential, which means it breaks out on its first failure and returns a failure out. So if so the turret watch is made up of a couple different sub goals. First of all, the watch 4, which checks to see if the target is in the specified target is within the specified range. If it is, it returns complete success, and so it'll move along down. The turret watch will move down its sub goal list. If it fails, it breaks out without going to the next sub goal, breaks back into the brain, and defaults to turret patrol. If the watch is successful, then it moves to the fire at goal, which has the turret rotate to the target and fire. And since that's a success, this will just finish out. It will, because the turret brain has hit a success, it'll break out and be done. And then the next update, it'll come back into the top of the turret brain, check for the turret watch again. So that is, like I showed you in action, pretty simple. The way it works out, a little difficult to describe without having the visual representation of it all. But from the user side, it's pretty simple. All we have is the AI turret here. We defined a couple methods that the goals need to use, and then all we need to do is declare it as an AI actor. From there, the only thing we have to do is add the goal. In this case, our turret brain is the top level goal, and register for AI. Then when we leave, we remove goals, which deletes all the goals that we've created. Once you add a goal, it then becomes owned by your internal behavior tree. So the remove goals make sure all the goals and sub goals it's created are deleted properly. And that's pretty much just it. So I've also updated my documentation here. Things are a lot, maybe not a lot, things are more organized than they were at the end of last quarter. So we have the welcome page here that just describes the basics of the engine. The setup code here deals with the basics of what you need to get going in the engine, the user initialize, and the load resources file. From there on down the list, it we talk about basic items. So basic game object, what is it? How does it work? Some stuff to get it going, and then links to more complicated modules here. The scene, a similar thing. Here's what it is. Here's how you can do some basic things with it, and then links to more advanced features. Underneath that, code examples, I wish I had the ability to link downloads here, but obviously this is just HTML files. It's not hosted anywhere, so there's no way to web link. But I do have the full source code for the demos ranging from the update and draw all the way up to my AI actor demo here. We also have the modules here which describe things a little more in depth. So we can go into game object, look at, okay, so here's how you add an object to a scene. Let's say I want to learn about drawing in 3D, and here's a little bit of description on that. If I want to get a little more advanced, we have all these kind of things. Actor, input response, alarms, all the fun stuff. And then terrain is also a separate module all by itself, with the publicly available terrains, or the publicly available methods here, and the links to how to add a terrain properly. And then miscellaneous features, just the set next scene and the color vector, which I now remember I forgot to go over in my code. So the color vector is basically, I'll just load it up here real quick. Color vector. Okay, so the color vector is essentially a vector, as you could probably guess by the name, but instead of holding references to a point or vector in space, it holds the RGB, sometimes A, values of a particular color that you'd want to use. So it makes things easier on the user side to deal with 0 to 255 rather than 0 to 1 branches of vectors, and put the potential of getting confused between what's a vector that's actually a point and what's a vector that's actually a color. So I have color vector. That is what the visualizer now uses. When it comes time for the visualizer to pass it into the engine, then we have this asVect method that keeps an internal copy of what the equivalent of the 255 version would be in the 0 to 1 scale for the vector, and allows color vectors to be easily transferred when we want to deal with an engine subsystem. The other good thing about color vectors is that I can have this big old list of default colors: black, light gray, navy blue, all these ones, all the way down to lightish red, that can be automatically called and sent in whenever I need them to be. So that's that with the color vector. And then obviously there is all the classes documented in here in the website. But I think that's about it. A lot of work over the 2 quarters. Going into this engine diagram and just zooming out, you realize the sheer immense amount of garbage. It's just garbage that has happened over this quarter. And like you mentioned, the Piazza post, we don't even have that big of an engine compared to a lot of things. But I don't know. I enjoyed it. I liked this class a lot, and the level of challenge that managing a system this big had. So yeah, that's about it. Thanks for a great year, Andre.